Pluto, a distant and perplexing body, was once considered a single and genuine planet, a member of our planetary family. However, continuous disturbing verbalizations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with an astonishing revelation. They suggested that this cold world is on a potential collision course with Neptune. Yet, how could this happen? Moreover, what might be the consequences of such a massive event? Are we witnessing an enchanting impact fantasy? Or is there more to this impending cosmic episode? Join us as we explore the possible consequences of a Pluto-Neptune collision. Pluto, a former planet that was demoted to a more inconspicuous status, remains a subject of interest and study in the astronomical community. According to persistent calculations by leading experts, Pluto's orbit is perilously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are raising alarms about a potentially catastrophic collision between these two planets, which could pose a significant risk to Earth. But how is such an event even possible? Pluto's orbit around the Sun is remarkable compared to the other planets in our solar system. It takes an astonishing 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is characterized by its highly eccentric shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination of 17 degrees to the ecliptic plane. The path Pluto follows is significantly more erratic compared to the other planets. This inclination and eccentricity add layers of unpredictability to its orbital pattern. Perhaps one of the most fascinating aspects of Pluto's orbit is its relationship with Neptune's orbit. For at least 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune. Contrary to what we might expect from their positions in the solar system, this leads to the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The evaluation of Pluto's orbit began shortly after its discovery. Initially, astronomers attempted to comprehend its astonishing path. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stood out with its dangerous inclination and unpredictable shape. The mystery surrounding Pluto's orbit can be explained by the three-body problem in celestial mechanics. This involves understanding how three objects in space, like Pluto, Neptune, and the Sun, move and interact with each other through their gravitational forces. It's akin to predicting their movements based on their starting positions and mutual gravitational pulls. In Pluto's case, this problem reveals how its orbit, Neptune's orbit, and the Sun's gravity interact in a complex way. Terms like apsidal libration, scope libration, and the VZK wobbling are fundamental to this discussion. According to astrophysicists, what's keeping all planets in their orbits is a form of libration. In the case of Pluto and Neptune, this term means that when Pluto crosses Neptune's orbit, its position is generally about 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or another giant planet, it is positioned far above their orbital plane, adding an extra layer of protection from potential collisions. Another critical factor in this scenario is the VZK wobbling, named after three researchers VA, LV, and KU, who studied how objects move in space. This wobbling effect explains why Pluto's path near the Sun is so peculiar. Despite the apparent randomness, this effect helps maintain Pluto's orbit stability over incredibly long periods. The VZK wobbling demonstrates that, despite the seemingly chaotic nature of space, specific patterns and forces help keep everything in order. These factors help safeguard Pluto's orbit, ensuring it doesn't collide with Neptune or veer off course. This three-body problem influences how we understand these orbits, particularly how space objects pull on one another. Focusing on this helps us study Pluto, our neighboring planetary system, and distant stars and planets. Numerical simulations in the late 1980s revealed that, despite these erratic properties, Pluto's orbit is still stable, with small deviations in initial conditions leading to significant differences over long periods. However, These odd characteristics of Pluto's orbit have been found to maintain consistency over incredibly long timescales. Later computer models have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, affect Pluto's orbit around the Sun. Neptune has a fascinating relationship with Pluto, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps keep Pluto's orbit stable. However, Neptune is not the only player. Jupiter's gravity also plays a crucial role in stabilizing Pluto's orbit, and Saturn contributes as well. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a consistent course for a very long time, possibly even billions of years. Perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue orbiting safely in space without running into trouble. These anomalies are essential in the broader context of the universe for maintaining the stability and consistency of celestial bodies. Without these factors, our solar system, as we know it, would be a place of far greater chaos and instability. Bodies like Pluto could indeed collide with others or be flung away from their stable orbits, triggering a cascading effect on other celestial bodies. For Pluto, particularly with discussions about it potentially colliding with Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the dynamic nature of neighboring planetary systems. The case of Pluto shows how even in the most seemingly unstable orbits, a balance can be achieved through the intricate interplay of gravitational forces and orbital mechanics. It also highlights the importance of constant observation and analysis of these anomalies to better understand our place in the universe. Exploring the depths of space often forces us to confront the enigmatic nature of celestial bodies. Pluto's orbit is a perfect example of this complexity. The probability of orbital resonance, which suggests the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or velocity can significantly alter its long-term orbit. Using virtual simulations has been pivotal in unraveling how Pluto moves through space. These models employ intricate mathematics to replicate how Pluto and other space objects, like Neptune, gravitationally interact. By tweaking small details in the simulations, astronomers can observe how even minor changes can profoundly impact Pluto's eventual trajectory. In the late 1980s, these simulations uncovered something intriguing about Pluto's orbit. Despite possessing mechanisms like apsidal libration and scope libration to stabilize it, its orbit can still be remarkably sensitive. A slight variation in Pluto's initial position or speed can, over many years, lead to a vastly different path. Despite this apparent chaos, Pluto's orbit remains stable over billions of years. This suggests that Pluto's journey around the Sun has an inherent order, even though it appears tumultuous at first glance. Understanding such unpredictable orbits, especially Pluto's, presents significant challenges. The inherent nature of these systems implies that long-term predictions are often fraught with uncertainties. While numerical simulations are invaluable for understanding and forecasting the future behavior of celestial bodies, they also highlight the limits of our predictions. These models heavily rely on the precision of initial conditions and the complexity of the interactions they simulate. Any slight error or deviation can drastically alter the outcomes, making precise forecasts extremely difficult. The chaotic nature of celestial orbits, like Pluto's, serves as a reminder of the ever-changing and dynamic nature of the universe. While we've made significant strides in understanding space, Pluto's case reminds us of the limitations of our knowledge. Grasping the gravitational influences of the giant planets on Pluto's orbit offers profound insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have far-reaching implications for the stability and trajectory of other bodies within the system. So why are prominent astrophysicists suddenly raising concerns about a potential collision between Pluto and Neptune? Despite all these intricate forces working to prevent such an event, Neil deGrasse Tyson, a renowned astrophysicist, offers a nuanced perspective on the mysteries of our solar system, particularly the captivating example of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's fascination with the overlooked corners of space. His stance on Pluto's reclassification is framed within the ever-expanding knowledge of our solar system. He views the reclassification not as a diminishment but as a meaningful shift aligned with our growing understanding of the numerous bodies surrounding our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He sees the complexity of Pluto's orbit and its interactions with Neptune from a perspective that acknowledges the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant changes in the future. This possibility serves as a reminder of how much we still have to learn about the forces shaping our planetary system. In the grand scheme of things, Pluto's orbit is a captivating case study in the intricate interplay of gravitational forces within our solar system. While its orbit is stable at present, the mysterious dynamics between Pluto, Neptune, and the other planets suggest that even the most seemingly stable orbits could change over time. As astrophysicists like Neil deGrasse Tyson continue to probe the mysteries of the universe, they help us better understand the delicate balance governing the movements of celestial bodies. The potential for a Pluto-Neptune collision isn't necessarily imminent, but it serves as a reminder of the constantly evolving and complex nature of the universe. Regardless of the established theories surrounding Pluto's orbit, it's essential to consider the broader implications of these forces for how we understand the solar system and the cosmos at large. While Pluto's journey is one of fascination, it is also a reminder that the universe is filled with mysteries and complexities waiting to be explored. The concept of orbital resonance, particularly between Pluto and Neptune, is a central piece of this puzzle. This resonance, where the ratio of Pluto's and Neptune's orbits is 2:3, is a crucial aspect of celestial mechanics. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance ensures that despite their orbits crossing, the 2 planets never collide. This is a result of the gravitational interactions that stabilize their paths, working together to prevent any catastrophic impacts. The importance of resonance in maintaining stability cannot be overstated. It provides a striking example of how systems in space, even those that initially seem chaotic, can self-regulate through subtle gravitational forces. Understanding this resonance also explains why Pluto, despite its irregular orbit, has remained stable for billions of years. This dynamic is a vital part of the larger framework of the solar system. The influences of planets like Jupiter, Saturn, and even Uranus are crucial in maintaining stability in the orbits of smaller bodies like Pluto. Jupiter, with its immense gravitational force, acts as a sort of guardian for the solar system, affecting the orbits of other asteroids and dwarf planets, including Pluto. In fact, some experts speculate that Jupiter's gravity may have prevented Pluto from being ejected from the solar system entirely.